What is generative modeling? Generative modeling can be broadly defined as follows. Generative modeling is a branch of machine learning that involves training a model to produce new data that is similar to a given dataset. What does this mean in practice? Suppose we have a dataset containing photos of horses. We can train a generative model on this dataset to capture the rules that govern the complex relationship between pixels in images of horses. Then we can sample from this model to create novel, realistic images of horses that did not exist in the original dataset. This process is illustrated in Figure 1.1, which can be found in the bonus PDF. In order to build a generative model, we require a dataset consisting of many examples of the entity we are trying to generate. This is known as the training data, and one such data point is called an observation. Each observation consists of many features. For an image generation problem, the features are usually the individual pixel values. For a text generation problem, the features could be individual words or groups of letters. It is our goal to build a model that can generate new sets of features that look as if they have been created using the same rules as the original data. Conceptually, for image generation, this is an incredibly difficult task, considering the vast number of ways that individual pixel values can be assigned and the relatively tiny number of such arrangements that constitute an image of the entity we're trying to generate. A generative model must also be probabilistic rather than deterministic, because we want to be able to sample many different variations of the output rather than get the same output every time. If our model is merely a fixed calculation, such as taking the average value of each pixel in the training dataset, it is not generative. A generative model must include a random component that influences the individual samples generated by the model. In other words, we can imagine that there is some unknown probabilistic distribution that explains why some images are likely to be found in the training dataset and other images are not. It is our job to build a model that mimics this distribution as closely as possible and then sample from it to generate new, distinct observations that look as if they could have been included in the original training set. Generative versus discriminative modeling. In order to truly understand what generative modeling aims to achieve and why this is important, it is useful to compare it to its counterpart, discriminative modeling. If you have studied machine learning, most problems you will have faced will have most likely been discriminative in nature. To understand the difference, let's go over an example. Suppose we have a dataset of paintings, some painted by Van Gogh and some by other artists. With enough data, we could train a discriminative model to predict if a given painting was painted by Van Gogh. Our model would learn that certain colors, shapes, and textures are more likely to indicate that a painting is by the Dutch master, and for paintings with these features, the model would upweight its prediction accordingly.